Transistors are connected in specific ways to create special circuits called logic gates. Logic gates can be combined to perform calculations, make decisions, and remember information. There are three basic gates: AND, OR, and NOT. We will focus on how these gates allow a computer to think or to compute. At the end of the program, and if you're interested, you may like to investigate how transistors can be connected to form each of these basic gates. Let's first look at the AND gate. The AND gate has two inputs and an output. The output is a 1 only if input 1 and input 2 are also 1. If either or both inputs are 0, the output is 0. It's easy to remember. Input 1 and input 2 must be 1 to give a 1 output. Anything else results in a 0 output. Now let's look at the OR gate. Like the AND gate, the OR gate has two inputs and an output. The output is a 1 if either input 1 or input 2 is 1. If both inputs are 1, the output is still 1. In fact, the only time the output is a 0 is when neither input is a 1. That's as complicated as it gets. The NOT gate is even simpler. The NOT gate has just one input and one output. The output is not the input. So if the input is 1, the output is 0. Likewise, if the input is 0, the output is 1. We've looked at the three basic gates, AND, OR, and NOT. How do we use these to do calculations or to make decisions? Let's look at a simple example, adding two numbers. The principles you'll see here are used to form the simplest calculator through to the most sophisticated supercomputer. Don't be alarmed by the apparent complexity of the circuit you're about to see. It is not necessary to remember the circuit to understand, and we will examine the circuit step by step. This complicated looking circuit is called an adder, and believe it or not, it can add two numbers together. It has inputs and outputs, just like the individual gates we were looking at a moment ago. To make things easier to explain, we're going to do two things. First, we're going to hide all the circuitry, so we can concentrate on just the inputs and outputs. Second, we're going to label the inputs and outputs to make the diagram easier to explain. Confused yet? Don't worry, this is going somewhere. In just a couple of minutes, you'll have proof that it is possible to build something useful out of a pile of transistors. The adder operates as follows. The two numbers we want to add, inputs A and B, the result is the labelled output. We'll look at the carry input and output in a moment. First, let's consider the addition of two digits. If we were describing decimal addition, we might decide to add 2 and 5. The result, of course, would be 7. But we're dealing with binary, so the only two digits we can add are 0 and 1. The possibilities are as follows. 0 plus 0 equals 0. 1 plus 0 equals 1. 0 plus 1 equals 1. What about 1 plus 1? Remember, we only have two digits, 0 and 1. In decimal, the addition of 9 and 1 gives us a similar problem. We have only the digits 0 to 9. The answer, of course, is that we carry the 1 to the next column. Most people will probably be familiar with this type of addition from school. In binary addition, the process is much the same. Let's return to the adder circuit and see how it performs this addition. We'll start with an easy one. 0 plus 0 is 0, and there's no need to carry anything. Easy. Let's look at another one. 0 plus 1 is 1, and again there's no need to carry. And of course the inverse, 1 plus 0, must also equal 1. Finally, and this is the tricky one, 1 plus 1 is 0, and we must carry 1. You've seen what an adder does inside a computer. It adds 2 bits together and produces a result, and a carry bit. But how do we get an adder from a complicated looking mess of logic gates? The answer lies inside the adder. The blue lines indicate the flow of electricity through the circuit. The result, of course, is 1 with no carry. Study the circuit for a few moments to see if you can understand what's happening. Don't worry if it's a little confusing. The goal of this video is not to teach you the specific details, but to give you a better understanding of how something as sophisticated as a computer can in fact be broken down into many much smaller, simpler chunks. We'll look at one more example and then we'll move on. Remember this one. We're adding 1 and 1. The result is 0 with a carry of 1. Have another look, and if you wish, you can examine this circuit more on the series website. Let's recap. We've learnt that transistors are used to build logic gates, and, or, and not. And we've seen how many of these gates can be combined to produce a circuit capable of doing something useful. In our examples, adding 2 numbers. Of course, in a real computer, the numbers are much larger than 1. The adder circuit we've just seen is designed so that many of them can be chained together to add larger numbers, with the carry output of the one adder being linked to the carry input of the next, and so on. In modern computers, 64 1-bit adders are chained together to form a 64-bit adder capable of adding 2 64-bit numbers. No matter which way you look at it, that's a lot of bits. Adders are not the only thing we can make with logic gates. We can make circuits that add, subtract, multiply and divide, count, compare 2 numbers for equality or relative magnitude, and remember bits or bytes. The microprocessor is responsible for running the software or applications you use each day, your email client, your web browser, and all the other tools you know well. Together with the operating system, be it Mac OS X, Windows or Linux, it is responsible for directing the behaviour of all the other systems of the computer. Your disk storage, your screen, your speakers, your keyboard, your mouse, printer, and anything else you connect. It's an enormous job, but fortunately we can gain a superficial understanding of how it works by looking at a simple model. In this model, you can see a number of different components. A clock, which is used to pace the microprocessor. A control unit, which is responsible for supervising the operations of all the other components. A set of registers, each of which can store a single number. In modern processors, these registers are each 64 bits wide. The program counter is responsible for keeping track of what step in the running program the processor is at. The arithmetic logic unit, which is responsible for doing math on and making comparisons between numbers. The adder circuit we saw earlier lives here. The system memory is where programs and data are stored while the computer is turned on. And the input-output control consists of circuits to allow connecting devices such as a keyboard, mouse, and screen. Linking all these different units are buses. Buses are simply parallel wires that allow transmission of many bits of binary data from one part of the computer to another. The microprocessor spends its entire life going around in circles. The cycle you see here is the fetch-execute cycle. By examining each of these steps in turn, we'll be able to better understand how the microprocessor works. We start with the fetch process. In this process, the clock emits a pulse that tells the control unit to begin the next cycle. The control unit instructs the program counter to place the number of the next step of the program on an address bus. It also tells the system memory to place the instruction with that number on the data bus. Finally, the control unit records the instruction. In other words, the processor fetches the next step of the running program from system memory. Next, the decode process. This step involves only the control unit. The unit is responsible for decoding or understanding the instruction, figuring out how best to perform the operation requested in the running program. The execute process. The control unit sends special control signals to different parts of the processor to coordinate its activities, instructing the arithmetic logic unit to perform calculations and the registers to save the results. It also instructs the program counter to increment by 1, ready for the next fetch-execute cycle. Finally, the store process. The control unit directs the results of calculations to be stored back in system memory. It places the address of where the results should be stored on the address bus, and the data to be stored on the data bus. The system memory reads the result of the bus and saves it in the correct location. Then the cycle begins again, with the next step of the running program. A common clock speed in today's desktop computers is 3 GHz. A computer with a 3 GHz clock performs this fetch-execute cycle up to 3 billion times every second.